Hey, my name's Kyle. I'm the DevRel at Fhenix, and I'm just going to go over a quick overview of Fhenix kind of 101, building private applications with just pure Solidity. So real quickly, if you want to join the Discord, this is probably the best place to do it. I'll just leave this up here. Cheat sheet. This is probably the easiest way to get started. Again, we're standard EVM opcodes plus some FHE precompiles. I'll go into more of the details, but basically, if you can deploy your contracts on a standard EVM, you should be able to deploy to us. And again, we're FHE L2, so EVM compatible. But again, what is this FHE nonsense? FHE is basically a really fancy name for kind of doing, think about it like operations over ciphertext. So general homomorphic encryption is basically the ability to do something to one field and it affects another field. In this case, the plain text affects the ciphertext. And fully homomorphic encryption basically is the ability to run an infinite amount of these operations. So real quickly, FHE is kind of the new ZK. I'm sure a lot of you are familiar with the concept of using ZKPs for privacy. Some would say that's a meme. I don't know if I'd go that far, but there's a lot of nuance, I suppose, with it. So a quick overview of FHE. And again, I'm kind of saying FHE, obviously FHE and ZK are very different technologies. I see FHE as more like encrypted private operations versus ZK is more of like a constant time verification or just verification in general. Obviously, it's not always constant time, but anyways, I digress. Here's kind of like a timeline of the last 40 years. Privacy homomorphisms have existed for decades. However, in 2009, Craig Gentry changed the game with this introduction of something called like bootstrapping, and then which is kind of a way to make the noise, because FHE uses noisy encryption. So basically, bootstrapping allows you to reset. I'm not going to go too much into the details here, but yeah, if you have any specific questions, please reach out. Again, so like FHE and ZK both provide some level of privacy. ZK is like the more scalable technology as of now. However, things are changing very quickly. In terms of composability, FHE allows you to have multiple private input and run an operation on top of these encrypted inputs, just encrypted fields in general. And again, this is all done on chain, doesn't have to be off chain and then just verified. So you kind of get in the sense where maybe you wouldn't really know what the prover is doing. In this case, you would be able to verify each operation itself. Again, so the main issue with ZK for privacy is that it just doesn't address the issue of being able to run an operation over ciphertext, which means at some point you're going to have to decrypt to run these operations. Again, not always necessarily true. I mean, there are certain situations where you could use some sort of like secret sharing or just a bunch of different other methods. But from a high level, it's, there's kind of issues with it when it comes to the concurrency. But anyways, digress. So real quickly, building with Fhenix for this hackathon, it's relatively straightforward. It can be done with a single input. Again, if you know Solidity, you should be able to pick this up relatively quick. For those of you that would prefer to use hard hat, this is kind of what we have going on right now. So you just have to set it up locally. There's instructions on the docs. Similar thing with the Remix plugin for some of you that might, visual learners prefer Remix. I don't know, but that's also an option. In the future, we are going to be adding Foundry support. There's a few reasons why it's been a little bit difficult for us to add it to our network right now. Some of the way that the precompiles are handled, but these FHE precompiles will be added to Foundry down the road. Currently working on it. So input. So basically, you can think of FHE, Fhenix. What we're doing here is that when you would normally have an unsigned integer that's queryable from everyone, now you basically have an encrypted unsigned integer, which is in this case you can see is basically passed in as bytecode. This bytecode can be formatted into something specifically called what we call an NEU8, which is basically an encrypted unsigned integer of bit length 8, which means you can represent up to 256 different numbers basically, and then we go up to the sizes up into 256. However, not all operations are supported after you get past 32 bit length, but anyways, so it's a good thing to try to recondition yourself here. Again, like with FHE, similar to some other things, maybe like some DSLs you might be familiar with, but like we have constant time code, which means, it acts like constant time code in the sense where you have to have a single code path, which means you can't really branch, right? Branching isn't something that's feasible here. So most of you might be familiar with the methodology on the left, the syntax of like the if-else syntax and kind of having the cases that way. And I like to think of it as like, however, if you look at what's on the right, this is how we do it. We have like a selector function, which is essentially like a multiplexer operation, which allows you to pass an encrypted Boolean and then assign the value based on like whatever the encrypted Boolean is. So I like to think about it that like FHE doesn't have conditional write, but it is conditional assignment. And so it's probably one of the trickiest ways to have to recondition yourself into the specific type of engineering. But generally speaking, most things are relatively the same to general Solidity development. Require statements are also slightly different in the sense where you have to use FHE require, but it's basically kind of what it sounds like in the sense where if you have an encrypted integer and let's say you want to revert if the encrypted integer is not equal to something or if it's less than something, this is basically how you'd go about doing it. Very similar to a normal require statement in Solidity. Conversion leakage is basically, I just like to think about it that if there was a plain text history of a somewhere, right, that means that at some point, if the number existed in plain text, that means it leaked to state, that leaked memory to state at some point. So in this case, as you can see, if you pass in a plain text and then go through the process of actually encrypting it, you're basically going to be leaking what the value of the ciphertext is. So generally speaking, it's ideal to make sure that the whole process is encrypted. So what is FHEOS? Over at Fhenix, like I said, we're building in L2. One of the other products that we're producing is a threshold service network. It's something different from like other FHE, especially things that are marketed such as like FHEVM, is that, they're basically, from my understanding is for the most part, they're using synchronous asynchronous decryption or moving towards asynchronous decryption. We're also moving towards asynchronous decryption. However, from a DevX perspective, it's going to look similar as it does now in terms of the decrypt. Versus having to go through the process of making essentially what is like a cross-chain Oracle request and waiting for the response via callback function. But this threshold service network, you can kind of think of it as the MPC KMS that essentially handles the decrypt conditions of these ciphertexts, right? Because you don't necessarily want that to be just completely involved in your network for a few reasons. Partly security, partly scaling, etc. But again, I digress because that's not super pertinent to this hackathon. Phenix.js is basically the JavaScript library that's going to allow you to interact with Phenix essentially. So I won't get too caught up with the fact that it's like a new JavaScript library. Relatively, it's somewhat straightforward. It's actually, in my opinion, it's very similar to like standard stuff that you've worked with, right? This is basically just impacting your ABI interactions in the sense where we're going to handle with permissions, and I'll get to that in a second. But as you saw before in the encrypted inputs, right, you can't just pass in the number 5, right? Let's say you have to encrypt the number 5 to be a EUINT, for example, an encrypted integer. And so basically the Phenix.js here is kind of handling that for you. It's abstracting away a lot of the stuff, and it can really be done in, like, as you can see, that one line of code right there where you're basically just encrypting 5. So what are permissions? I talked about permissions, but basically it's the encrypted fields who has access to view these encrypted fields. So like I said, there's encrypted integers, and let's say part of your application, you need, a certain party to be able to view a value for whatever reason, or maybe you want to check your own value. So what you can do right here is you can basically, import the permissions library, and from the permissions library, you can create this thing called the permission object, and the permission object allows you to create, it's sort of like a modifier, if you would, on this specific function. And it's basically checking to see that the person that the message.sender actually is the correct person who has access to view this. So what's happening under the hood is it's basically kind of like we're decrypting and then we're re-encrypting with the specific user's pub key here. And so it's making sure it's checking to see that the pub key, the user is actually trying to view this, the message.sender, if you would, actually has the correct pub key access. So again, we can go into a lot more detail about the nuance of this, but this is just kind of a high-level overview. Here's an example permission, and again, conditions can be added. So for example, if you're part of a certain array, then you're allowed to decrypt a certain field text. But there's a lot of ways that can branch, and that's one of the beautiful things about Phenix is that it allows you to have very conditional re-encrypts or sealed outputs, if you would. So here's the sample smart contract. We have more in our docs. We're hosting a 5K hackathon. So if you're interested, we're looking for full stack applications. If you have any questions, feel free to reach out to me. General runtime tips are that, if you don't want your operations to overflow, essentially there are certain limits to each block. You can find that in the docs, but the important caveat to remember here is that basically there's two distinct things that are going to impact your gas calculations, and it's going to be what operation you're running. For example, division is going to be more expensive than addition. And what size bit length you're using, right? So like adding to 8 bits is going to be cheaper than adding to like 16 or 32 bits, right? That's just sort of basic engineering. And so here's a pro tip from our developers is that like if you get stuck, you know, GPT is actually pretty solid for coming up with some stuff. You know, it's probably worth a try. And yeah, I just wanted to say thank you. If you have any specific questions, feel free to reach out to me. My Telegram's at Corsula26. I like the Pokemon. So yeah, thank you for your time and look forward to hopefully working with you. All right, take care.